The algorithm for the Lagrange interpolation is given on the left-hand side. You can see here we have a function simply with data x and y, and is the degree of Lagrange polynomials. And basically the degree defines the Lagrange term. You can see here the difference, a division of it, and the product. Product basically is being added by summations to be able to get the Lagrange term in different n values or degrees. And this xx is basically the value for which we want to find the function value. So we will find the result of this using the interpolation. This is a very simple process. You can just use, for example, Matlab to code, have a code of this as an algorithm. And so this algorithm is set up to compute a single nth order prediction where n plus 1 is the number of data points. And of course, there is an error of Lagrange interpolation as well. And the error is the same has the same formulation as the Newton's method. You can see here, in Newton's method, we said that we have the difference and also these values. In here also, just these values are the product of, so because we are using the Lagrange form, let's say alternative, we will have this product version. And to be able to predict this error, we said in the Newton's polynomial in chapter 15 that we are using an additional data point, xn plus 1 here, because we don't know x. Actually, the function value of x, we don't know it. We need to find it. That's why we cannot use this. But if we have an additional point for which we know the function value, we can simply, instead of x, we can use this. And an error estimate can be obtained this way, which is the same as Newton's method. We mentioned that in the Newton's method in detail. You can go back there and check it, and it is similar. However, because the finite divided differences are not employed as part of Lagrange algorithm, this is rarely done for the Lagrange. So for Newton's, prediction is done by using this, but for Lagrange, they don't consider it simply. Let's compare the Newton's polynomial and Lagrange polynomial for interpolation. Both of them have some advantages, but they give the same result for the same degree. We mentioned this before. And advantages of Newton interpolation. Let's check that first. The order of the polynomial is unknown. If it is unknown, the Newton's method has advantages because of the insight it provides into the behavior of the different order formulas, basically. And the error estimate can be usually integrated easily into the Newton computation because the estimate employs a finite difference. So because it is using finite difference as an estimation of the derivation, it has a better approximation of error with the error function that we mentioned in the previous slide. And therefore, for exploratory computations, Newton's method is often preferable. But the Lagrange polynomial has some advantages as well. When only one interpolation is to be performed, the Lagrange and Newton formulations require comparable computational effort because they give the same result and they have the same order. The computational effort is comparable. However, the Lagrange version is somewhat easier to program because it has just simply a summation of the Lagrange terms by the function values of the data. And the Lagrange form is often used when the order of the polynomial is known as a priori. So if we know the polynomial order, or if from the beginning we set the order of the polynomial that we want to use in the interpolation, then Lagrange is more preferable because it doesn't require computation and storage of divided differences. But if we are not sure about the order of the polynomial for the interpolation, then it's better to use the Newton method because the error estimate can be used to be checked if the error is getting smaller and smaller when we increase the maybe the order of the polynomial. Then at some point we can stop because the error is very low, and we can decide that okay, this is our order now. So for determining the order for exploratory, that means exploratory computations, we are checking different orders. Newton's method is better. And if we know the order, because the formulation is easier to program, Lagrange interpolation is a better choice. Here we have an example for Lagrange interpolation by computer. And we measured data for velocity of the parachutist example that we saw since the beginning of this course. And now our problem is to estimate the velocity of the parachutist at t equals 10 seconds. And we actually had some measurements. On the right hand side you can see for 1, 3, 5, 7 and 13 seconds we measured these values, but we don't know what is the velocity when it is 10. So basically when t is 10, what is v10? We don't know this and we want to solve it, and for this we will use polynomials of orders of 4, 3, 2 and 1 based on the pseudocode of Lagrange interpolation and compare the results. Let's check the results here. You can see all different order. Actually you can just use the pseudocode that we gave in the previous slides and have your Matlab code, then define this data and have the interpolation using the Lagrange interpolation. These are the data you can see, and this is the first order fit. Basically it fits because for first order we need only 2 data, and because this is in between 7 and 13 we use 7 and 13 to fit a linear data. So it directly passes through this 13 and 7 points. That's why it doesn't predict well the remaining points, the points before that. It's just basically using the last 2 to fit a line, let's say. In the second order we have 5, 7 and 13 because we need this in between of the data again. So 5, 7 and 13, for those the polynomial should be passing through this data but cannot pass through the others. Maybe it can if it can predict well, and you can see that it actually goes well with this. But these 2 are being extrapolated because we are just using these actually. And in here you can see that it's a very good prediction, especially for 10. You can see, maybe we can plot the values of 10 here. The value is somewhere here, and for this as well, 10. And we actually expect a value in between these 2. So this is an expected value. This can be somewhat expected value as well. But when we fit a third order, which includes this term again as well, so 4 terms, this one, this one, this one, and this one. So the function should pass through all of these, but not this one, not necessarily this one. And you can see that it's not able to predict this well. And for t equals 10, it actually goes a little bit high, then goes down. Instead of having a value of in between, I mean a smooth, this is very smooth. This is linear smooth. But in this it went up a little, which may be not expected. Or maybe expected because it's making a peak, then falling down actually. So this is the result, maybe like about 5,000. Here maybe 4,000, not much. Like this. Finally, in the fourth order, we are using all data to fit a polynomial of fourth order of Lagrange function, and we use all the data, and you can see it has to pass through all the data you can see here. But what we see is that this function actually is making a peak, very, very distinct peak. Instead of going like this, we were expecting a smooth one like this maybe. It's going a little bit more higher, let's say. And you can see for 10, it's very high, and it's about 6,000. It increased the value. So this may not be, maybe like this. This may not be a very good prediction because it's going very high. So maybe sometimes fitting a higher order polynomial may not be very good, and a lower order can be better. So it seems like second order is the best here, I think, to be able to predict 10 and also the others. So let's summarize these, the lower the order, the lower the estimated velocity at 10 seconds. It's the highest, some lower, and the lowest here. Higher order polynomials tend to overshoot the trend of data. So this higher value means it's actually overshooting, so not predicting very well. And first and second order versions are most appropriate according to these results, and because we were expecting a value in between these, not like going up and down like this. Maybe this is much better, maybe, but we are dealing with uncertain data, so regression would be more appropriate. So here, because we are having measurements, we can have some errors, and that's why we can have some up and downs, like uncertain. So a regression that fits all, like this, maybe we can show with blue, maybe like this. Maybe like this, a regression can be better to be able to have a result because we have an uncertain measurement data. So this is a good example that you can also solve in Matlab and see the results. Maybe you can increase the degree more, but you need more data for it. Actually, for this 1, 2, 3, 4, 5 data, you can up to 4 you can fit some polynomials.